So far we've looked at making graphs of univariate data. We've also looked at analyzing the graph's qualitative characteristics such as shape, center, and spread. Now we're going to move into describing the distributions numerically, putting a quantitative analysis to these. Here we're going to be most interested in the quantities of center, spread, and the position of different data points inside the distribution. The objective of the next few videos will be to take our discussion of graphs from a qualitative to a quantitative explanation, in which we will be discussing numerically how we determine the center, how the data is spread out, and the relative location or position of individual data points. We will continue that discussion with how changing the units that data is measured in affects the summary statistics. I think it's important to start off by introducing you to some of the symbols that we'll be using not only in the next few lessons, but the class as a whole. First, we're going to include X as any individual data point. The sample mean will then be represented by X bar. Now, a sample is a subset of the population. The population mean we're going to allow to be the Greek letter mu. A sample standard deviation will be represented by the letter S, and the population standard deviation will be represented by another Greek symbol, the lowercase sigma. More generally, the next symbol, uppercase sigma, is in mathematics meaning the sum of, to sum up whatever comes after it, to add them together. N we will allow to be the number of data points in a given data set. The first measure of central tendency will be something we're all familiar with, the mean, or the numerical average. The mean is reserved for normal, mound-shaped, symmetric distributions. It should be noted that it is sensitive to extreme values, that is, outliers or values that lie low or very high on the data set can pull the mean off of what we would consider to be the true center of the data. Therefore, mean, we say, is not a resistant statistic. It is not resistant to extreme values. We've all had experience calculating the mean, and the next video will go into more specifics of the actual calculation. Our next measure of central tendency is another one you're probably familiar with, the idea of median, the middlemost data point in a set of data that has been placed in numerical order. It is the best selection for a non-normally distributed data set. A data set with skew or extreme values, we will use the measure of central tendency known as the median. The median then is said to be resistant to extreme data points and skewness. Looking at example 1, we have a data set with an odd number of data points. When we do a median calculation then, we see that by crossing out all the values high and low, working our way towards the center, we end up with a median value of 11. Here in example 2, this data set has an even number, lends itself to an interesting problem. As we cross off high and low values, we end up with 6 and 8 as the central values. When this happens, we use mean of the two values. In example 2, our median would be 7. In the the last video we discussed the idea of graphical characteristics. One of those main ideas was the idea of skewness, a graph that's been skewed to one side or the other. Here we see three graphs. Graph A, skewed negatively. Graph B, no skew at all, normal and mound-shaped. And graph C, a graph that is positively skewed or skewed to the right. Let's take a look now individually at these graphs and see how that affects their mean, median, and mode. Now I know we didn't talk about mode. Mode isn't really that terribly interesting in AP statistics. Mode is just the most frequently occurring value. Therefore, in a histogram, as we're looking at here, it would be the one with the tallest peak. Looking at our graph A, we see that mean is pulled further away from median and mode, further away from the center of this distribution, because we know that mean is not a resistant statistic. Median value is pulled somewhat off of the highest point of the mound, but again, with this type of distribution, we would consider the median to be the most appropriate measure of central tendency. In B, we see that we have a graph that is normal and mound-shaped. Mean, median, and mode are all located at the same spot. In graph C, we see a distribution that is skewed positive or skewed to the right. Here, the mean has been pulled off of the center, again, the most. Mean is not a resistant statistic. It is not resistant to those extreme values on the high side of this distribution. Median is once again pulled somewhat slightly off of the mode, but median is the value I would use to describe the center of this distribution. Now it should be noted that the shape of the graph does imply the relationship between mean and median. This is a favorite question on the AP test, multiple choice, to ask about the relationship of these three variables on a graph like this. However, it should also be recognized that the converse not be true, because mean and median are set up higher or lower of one another does not mean that we're looking at a skewed graph. Can you think of a graph that is not skewed but has a mean and median set up in one of these ways?